Okay, this week we are going to be dealing with probability and compound events. We're going to talk a little bit about independent and dependent events. We're also going to talk about experimental probability versus theoretical. Theoretical is, for example, what is the probability that if I roll a number cube or a die that I'll land on the number 2? Well, that's 1 over 6. That's what we call theoretical. But experimental probability is when I actually conduct experiments and then I try to maybe predict what's going to happen in the future based on that. And what you'll find sometimes is that your experimental probability doesn't always match up with your theoretical. For example, I may roll you would think that it might take you 6 times to roll the number 2 on a cube, or sorry, a die, but you might end up rolling it on the first try. So, sometimes these don't match up. What I want you to remember is on a long enough time frame, if you do enough experiments, that at some point, for example, flipping a coin, you may flip a coin 10 times and it lands on heads 7 times. Well, we all know the theoretical probability is that if we do it 10 times, it'll land on heads 5 times. Well, 10 is not a very, very big experiment, but on a long enough time frame, if we extended that to 1,000 rolls, and it still may not be exactly 50-50, but you'd probably be closer to 499 and 501 or 498 and 502 or something like that. So the more experiments you do, the closer you're going to get to your theoretical probability. Now, number 1, Dan rolled a number cube or a die, I don't know why they call it number cubes for, 20 times, and it landed on the number 3 6 times. So we have 6 out of 20 times it landed on the number 3. What is the experimental probability? What is the experimental probability? In other words, based on this, that Dan will roll a 3 the next time he rolls a cube. Well, it's simply this, but we need to reduce it to 3 over 10. Now, in reality, it should be 1 over 6, but the experimental probability, based on what has happened, is 3 out of 10 or 6 out of 20. The theoretical would be 1 out of 6. The theoretical is 1 out of 6. The experimental is 3 out of 10. Now, just like I was saying before, which best describes what would likely happen if Dan rolled the number cube another 80 times? So again, we're making our experiment bigger, and the bigger we make it, again, the closer it gets to the actual theoretical probability. There would be no change. Well, more than likely there would be a change. B, the experiment probability would get farther from the theoretical probability. Again, the more we do, the closer it's going to get to the theoretical. C, the experimental probability would exactly match the theoretical probability. Maybe, but not likely. It's not always going to be exact. It's going to be very close, but not exactly. And finally, D, the experimental probability would get closer to the theoretical probability. Choice D. Sonia wrote each letter of Ledbetter on a separate index card. So we had one with L, one with E, one with D, one with B, and so on and so forth. She picked one letter at random and put the card back and then repeated the experiment. If she performed this experiment 90 times, which is the best prediction of the number of times that Sonia would pick T? Well, the theoretical probability, what we're always going to do is put the number of times that could happen over the total number. So in this case, we've got 2 for 2 T's over 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. Okay? Which is the best prediction for the number of times that Sonia would pick T if she did this experiment 90 times? Well, if we did it 90 times, we could expect something here. Okay? So basically what we would have is we could set a proportion. Again, a lot of this class, I've told you, you can solve about 25% of, well, maybe not 25%, maybe 15% of all your math problems with proportions. This is going to be 9x equals 2 times 90 is 180. We're going to divide both sides by 9. This is eliminated. Just take my word for it. You can do the math yourself. 80 divided by 9 is 20, which is choice B. Blake tossed a coin 80 times. The coin landed on heads 60 times. Now that could happen. What is the experimental probability that Blake will toss heads? If it landed on heads 60 out of 80 times, the experimental probability would be 60 over 80, which is 6 over 8, which is 3 over 4. But we all know the experimental probability isn't always exactly the same as the theoretical. The experimental probability, is it greater or less than the theoretical probability? What's the theoretical probability? The theoretical probability is 1/2. Okay? The experimental is 3/4. So the experimental probability is higher. And again, maybe if we did 800, we would get closer to 1/2, which would be 400 and 400. Or somewhere close to it, 401 to 399 and so on. Okay. The Skate Pro company manufactures skateboards. They found 12 defective skateboards out of a batch of 400. How many defective skateboards might they find in a batch of 1,200? Well, again, we can set up our proportions. If 12 out of 400 were bad, we can predict what's going to happen with 1,200. So we would multiply. This would be 400x equals, and you can do this math yourself, but 1,200 times 12 is going to be 14,400. Okay, now we've got a one-step equation. We're going to divide both sides by 400. And again, I'll let you work the math out. You're smart 7th graders now. You should be able to figure these out. But if you divide this by this, the answer is 36. So the answer is 36 skateboards will be defective. Okay. Now we're going to move on to compound events. These are significantly more complicated, but if you can remember the rules, you can certainly figure out how to do this. And the best ones we do usually with a die and a spinner, or two spinners that are a little bit different, or something along those lines. We're going to skip number 2, and we'll do number 1. What is the probability of spinning 3 on both spinners? So basically what you're going to have is a probability of spinning a 3 and a 3. Anytime I'm asking you the probability of something and something, and is always going to be multiply. You're going to multiply the two probabilities together. Because if you're asking for this and this, you're asking for two fairly unique things to happen at once. And usually when you multiply, or not usually, when you multiply fractions, they're going to get smaller. Okay? So the probability, for example, of tossing a coin and landing on heads, and then tossing a coin and landing it on heads again, it's 1/2. The probability of the other one landing on heads is 1/2. But you have to multiply to find the probability of both of those happening at the same time so that the probability drops. Well, the same thing goes here. What is the probability of spinning a 3? Well, we have to say the outcome, which is 3, and there's 2 of those for a possibility of 5 outcomes. And then over here, what's the probability of rolling a 3 or spinning a 3? 3 out of 4. The word and, or even though it's not in there, we know that that's going on. And it's, basically the question is asking, what's the probability of spinning a 3 and a 3? So of course we're going to multiply, and we do that straight across. We got 6 over 20, which reduces to 3 over 10. The probability is 3 and 10, and you can reduce that. If you can make that into a percentage, if you like, you make that 30%. Gabriel is doing a probability experiment. He is tossing a coin and spinning a spinner with 4 equal sections. So we've got a coin, and then we got a spinner here. And forgive my math, or forgive my artwork, but we have a spinner here, and spinning this dude and trying to get it to land on 1 of 4 sections. And they're numbered 1, 2, 3, and 4. So how many possible outcomes are there? Well, we can simply multiply the possibilities together. We can say the possibility of landing on heads, or there are 2 choices for heads and tails. It's heads or tails, that's 2. The answers over here are 4. The possibilities are 4 for 8. And how this works is a possibility, if it lands on heads, you can spin a 1. If it lands on heads, you can spin on 2. Lands on heads, you can do a 3. Lands on heads, you can do a 4. Or if it lands on tails, you can do a 1. Lands on tails, you can do a 2. Lands on tails, you can do a 3. Lands on tails, you can land on a 4. 1, 2, 3, 4, 5, 6, 7, 8. But you can simply multiply the outcomes together. And you can do this with 2, 3, 4, 5, 10 different independent events. And by the way, this is an independent event. And the reason why I say that now is because if you toss a coin and it lands on heads and then you spin a spinner, those two events do not have anything to do with one another. The fact that you tossed a coin on heads does not affect the spinner in any way. It cannot possibly affect it. Now, let me give you an example of a dependent event really fast before we move on to it. I've got a bunch of socks here in a drawer, and the ones on top here, these are all blue or black, and these are all white. Okay? Let me make a better picture. I got a drawer. I got socks. They're all separated, by the way. I got white ones. I got black ones. What's the probability of me pulling out a black sock and then a black sock? Well, if I don't replace the black sock. So, for example, what's my probability, and this is fairly easy, the first one, what's my probability of pulling out a black sock? Well, it's 1/2, or, 4 out of 8. Okay. But I don't replace it, so that's gone now. Now what's my probability of pulling a black sock? Now I only have 3 to choose from out of 7. And so I would multiply those together to get 3 out of 14. These are dependent events. In other words, the outcome or the probability of the second event is dependent on what happened on the first one. Okay? That changes my probability altogether. Therefore, it's going to be a dependent event. And I'm sorry I moved that over here. Okay? So I want you to keep that in mind as we go forward. There are 4 boys and 2 girls from the 7th grade and 3 boys and 5 girls from the 8th grade on the soccer team. Coach Hart will pick 1 captain from each grade. What is the probability that both captains will be girls? All right, well, what's the probability of him picking girls from the 7th grade? All right, well, we have girls. We have their possibility of 2 girls out of a total of 6 kids. So that's the probability of getting a girl. Then we have to multiply that by the probability of getting a girl out of the second one, which is 5 girls out of 8 total kids. You're going to multiply those together to get 10 over 48. That reduces to 5 over 24. Again, basically what I'm saying is, and even though the word "and" isn't in here in this context, it says, that question is saying, what is the probability of me choosing a girl and a girl? Okay? Even though they're independent, this is where we're going to multiply. Choice A. Alexis tossed 2 dimes in the air. What is the probability that both dimes will land on heads? Well, what's the probability of getting 1 dime on heads? 1/2. What's the probability of the other one? 1/2. Basically, what I'm saying here is, what is the probability of rolling a dime and a dime? Remember, and means multiply, so we're going to have 1 over 4. Choice C. Wendy is going to toss 2 number cubes, not 1 but 2. And basically that's a die. I have no idea again why they call them number cubes. With faces numbered 1 through 6, just like a regular die, and a coin. How many possible outcomes are there? Again, well, there are 6 for the 1 number cube, 6 for the other, and 2 for the dime or coin. We multiply those together. This is 36 times 2. This is 72. And forgive me for marking this out, but I was gonna forget it because I made such an egregious typo. But here I'm gonna go again. Patrick and Austin had a penny and a number cube at the same time. So there's a penny and a number cube. Are the events dependent or independent? Let me ask you a question. If I tossed a coin and it landed on heads, does that have anything to do, does that affect in any way the number cube or the die? No. Okay, this is not like the sock experiment. Or another experiment that's dependent is, well, we have a bunch of marbles in a bag and we pull one out and we don't replace it. So the probability of the first event is one thing, but then the probability of the second event changes because we remove one of those. That is an example of a dependent event. These are independent, where one does not influence the outcome of the other. Finally, what is the probability that, it should be a penny, will land on heads and a number cube or die will land on a multiple of 3? All right, so we got to be careful with this. A multiple of 3, the only two multiples of 3 on a number die are 3 and 6. So there's two possible outcomes. So for example, let's talk about the penny will land on heads. The probability of that is 1/2. The cube will be something out of 6. Well, there's two possibilities. There's a 3 and there's a 6, so that's 2. And you can reduce if you want to, but this is 2 over 12, which is 1 over 6. And that, my friends, is 7th grade math.